Dear students, so in previous class we were discussing the Lipschitz condition and Lipschitz function. So what is the Lipschitz function? A function f is said to be a Lipschitz function if modulus of f of x minus f of y less than or equals k into modulus of x minus y. If any function f from a to r or r to r or maybe if it satisfies this condition, then that function f is said to be a Lipschitz function and k is said to be Lipschitz constant. We already see that when a function satisfies Lipschitz condition, it is uniformly continuous. But if a function is uniformly continuous, it need not be satisfies Lipschitz condition. Okay. So now here let us discuss about some properties or some of the important research. Means let f from a to r, a is any subset of r, and f from a to r is uniformly continuous. Is uniformly continuous on a, and xn, secant xn be a Cauchy sequence. Secant xn is a Cauchy sequence in a. Then f of xn is Cauchy in R. Then secant f of xn is Cauchy in R. That's an important research. If f is from a to r, where a is a subset of r, and if f is uniformly continuous, means modulus of f of x minus f of u strictly less than epsilon, provided mod x minus u less than delta. So how to prove this one? And our aim is, if f is a uniformly continuous function and xn is a Cauchy sequence in a given domain, then f of xn is also Cauchy in R. So the proof is immediate. Why? What is f here? F is uniformly continuous. F is uniformly continuous means f is uniformly continuous on A. F is uniformly continuous on A means if modulus of x minus u less than delta, then modulus of f of x minus f of u strictly less than some epsilon. So this is the condition for, or the criteria for uniform continuity of a function. This is the condition. F is uniformly continuous on A means for all x comma u fallen A. For all x comma u fallen A, then if modulus of x minus u is less than delta, then modulus of f of x minus f of u less than epsilon for all delta and epsilon are positives. Now what is given? It is given xn is Cauchy. Xn is Cauchy in A means, that means is modulus of xn minus xm strictly less than delta for all n, m greater than or equals a particular stage k itself. Okay. So instead of modulus of x minus u less than delta, here modulus of xn minus xm less than delta. Thus, in the light of this above argument, if modulus of xn minus xm less than delta, then modulus of f of xn minus f of xm strictly less than epsilon. Okay, modulus of f of xn minus f of xm strictly less than epsilon for all epsilon is positive. That means secant f of xn is Cauchy sequence in R. Okay, is Cauchy sequence in R. So when f is a uniformly continuous and the secant xn is Cauchy, then secant f of xn is also Cauchy in R. Agree? Okay. Now let us discuss about the continuous extension theorem. There is another important theorem. So the theorem is known as continuous extension theorem. Continuous extension theorem. So the theorem states that if a function f is uniformly continuous on AB. Statement is if f is uniformly continuous on AB, if f is uniformly continuous on AB, if and only if it can be defined at the end points A and B such that the extended function is continuous on closed interval A. If f is uniformly continuous on AB implies and is implied by the extended function or the function which is defined at the end point A and B such that the extended function is continuous on closed interval A. So how to prove? So theorem is important, statement is also. So it's a necessary argument. First we suppose that f can be defined on the end points A and B such that the extended function is continuous on closed interval A. Means first we suppose that f can be defined on the end points A and B such that the extended function is continuous on continuous on closed interval AB. That means f is continuous on closed interval AB. Okay, so extended function is continuous on closed interval AB means suppose f is continuous on closed interval AB. But the continuity need not be implies uniform continuity. But the continuity, if it is defined on closed interval, then it should implies uniform continuity. That means f is uniformly continuous on closed interval. F is uniformly continuous on closed interval AB. So f is uniformly continuous on closed interval AB means f is continuous. F is uniformly continuous on closed interval AB means f is uniformly continuous on interval AB. So the first part is finished. This is a necessary argument. First we suppose that f is continuous at the end points. The extended function f is continuous at the end points A and B such that the extended function is continuous on AB. Okay, first we defined f can be defined on the end points A and B such that the extended function is continuous on closed interval AB. The extended function is continuous on closed interval AB means the function f is continuous on closed interval AB. Clear? First we define, or suppose that f can be defined on the end points of closed interval AB such that the extended function f is continuous on closed interval AB. When the extended function f is continuous on closed interval AB, surely f is continuous on closed interval AB. But on closed interval, the continuity implies uniform continuity. So f is uniformly continuous on closed interval AB. That means f is uniformly continuous on AB. Agreed. So the first part is finished. Necessary argument is finished. What about the sufficient condition? Again, let's suppose that if f is uniformly continuous, suppose f is uniformly continuous on A. F is uniformly continuous on A. So let xn, the sequence xn be any sequence in open interval A, such that xn converges to A. That's our assumption. Xn is any sequence in AB such that xn converges to A. Clearly xn is a Cauchy sequence. Clear? It implies xn be a Cauchy sequence. Xn is a Cauchy sequence in AB. So sequence xn is Cauchy. Why? Because it is sequence xn is Cauchy. Sequence xn is Cauchy and f is uniformly continuous. Then we already proved that secant f of xn is Cauchy. Okay, secant f of xn is Cauchy by previous theorem. Xn is any sequence in AB with xn converges to A. Convergent sequence is Cauchy, so secant xn is Cauchy sequence. then surely since f is uniformly continuous, f of xn is a Cauchy sequence. F of xn is Cauchy sequence means secant f of xn converges. Cauchy sequence is always converges. So let secant f of xn converges to some L. Secant f of xn converges to L. Okay. Now let sequence UA sequence UN be any sequence in AB, sequence UN is a sequence in AB, such that sequence UN converges to A. You can, previous case, you can choose xn in AB, xn converges to A. Again, you can choose another sequence in AB which has converged, just a convergent point, A itself. Okay. So what about limit UN minus xn? Limit UN minus xn is limit UN minus limit x. By the property of limit, it is limit UN minus limit x. What is limit UN? E. What is limit xn? E. So A minus A equals 0. Okay. But what is f? Since f is uniformly continuous, it is given, and f is uniformly continuous on AB. F is uniformly continuous on AB. So that means the limit f of xn, since f is uniformly continuous on AB and the xn and the un are any two sequences in AB with the limit of un minus xn is 0, then what is the limit f of xn minus f of un? So it is limit f of xn minus f of un is also 0. Clear? F is uniformly continuous on AB, limit un minus xn is 0, and f is uniformly continuous on AB, limit of f of un minus xn is 0, means limit f of xn minus f of un is also 0. Okay. Consider f of un. Consider f of un. What is f of un? We have f of un equals f of un minus f of xn plus f of xn. Okay. F of un equals f of un minus f of xn plus f of xn. That means limit f of un equals, what is limit f of un? Limit f of un is limit of the first two quantities plus limit f of x. This one, f of un is this one. So limit f of un is limit f of un minus f of xn plus limit f of xn. What is this one? Limit f of xn minus f of un is 0. That means limit f of un equals limit f of xn. What is limit f of xn? We assume f of xn converges to L. So limit f of un equals limit f of xn. But limit f of xn is L. So limit f of un is L itself. Thus we get same value L for every sequence converging to A. Okay. So define f of A equals L. So you will define f of A equals L. F of A equals L. Then f is continuous at that means f is continuous at A. Okay. Similarly, we can prove that f is continuous at B. F is continuous at A. Similarly, we can prove that f is continuous at B. Then that means f is continuous on, or f is continuous on closed interval A. So this is the continuous extension theorem. Okay, the statement is also important. So the proof is so immediate. Clear? Now we try to solve a problem that is prove that f of x equals 1 by x square. F of x equals 1 by x square. which is uniformly continuous. Which is uniformly continuous on closed interval 1 infinity, but not uniformly continuous. Not uniformly continuous on closed interval 0, closed interval 0. F of x equals 1 by x square is uniformly continuous on closed to 1 infinity, but it is not uniformly continuous on closed to 0 infinity. That's an interesting case. How to prove this one? So how to prove it is uniformly continuous on closed infinity? Let f of x equals 1 by x square. Okay. So let x comma y fall in closed interval 1 infinity. Now, what about the modulus of f of x minus f of y? Modulus of f of x minus modulus of f of y means modulus of 1 by x square minus 1 by y square. Okay, equals modulus of x square minus y square divided by x square into y square. This can be rearranged as it equals 1 by xy modulus of xy into modulus of 1 by x minus 1 by y, or simply it is rearranged as what is x square minus y square? It is x minus y into x plus y. Okay, divided by modulus of x square y square or xy whole square. Sure. So, which equals 1 by xy into 1xy into it is modulus of x minus y. What it means? X plus y by x square y square. So it is 1 by x plus 1 by y. That's immediate. It is, this is y plus x, means x plus y into x minus y by xy into xy, x square y square. Okay, that is rearranged as in this way. X minus y is here, x what remains, and 1 by xy is also here. X plus y by x square can be rearranged as 1 by x plus 1 by y. X by x square means, sorry, 1 by x by y means 1 by y, and the remaining is 1 by x. Okay, means x plus y into x minus y by xy into xy means x square y square. Sure? Okay. So means, so it is less than or equals modulus of x2 into modulus of x minus y. Why? Because what is 1 by x? 1 by x fall in closed, sorry, x comma y fall in closed interval 1 infinity. X comma y fall in closed interval 1 infinity. Closed open 1 infinity. That means mod x less than or equals 1 and mod x is mod x greater than or equals 1 and mod y greater than or equals 1. X comma y fall in closed open 1 infinity. So mod x greater than or equals 1 and mod y greater than or equals 1. Means modulus of 1 by x less than or equals 1 and also modulus of 1 by y less than or equals 1. Okay. So it is 1 by x less than or equals 1, 1 by y less than or equals 1, 1 plus 1, 2. So it is, and xy, 1 by xy. What is 1 by xy? 1 by xy less than or equals 1. Okay. So it is less than or equals 2 into modulus of x minus y. That means we have modulus of f of x minus f of y. What do you get? That is modulus of f of x minus f of y less than or equals 2 into modulus of x minus y. We start from modulus of f of x minus f of y, which is less than or equals 2 into modulus of modulus of x minus y. 2 is known as Lipschitz constant. Okay. Means f satisfies Lipschitz condition. When a function f satisfies Lipschitz condition, it should be uniformly continuous. So that implies f is uniformly, f is a Lipschitz function, thus f is uniformly continuous on closed interval 1. Clear? So, but when the lower limit is 0, why it is not uniformly continuous on there? So, that can be proved by seeing a simple example. Okay. Put xn equals some x and y. Let xn equals 1 by root n and yn equals 1 by root n plus 1. 1 by root n, yn equals 1 by root n plus 1. Okay. So clearly, what is xn minus yn? Xn minus yn, 1 by root n minus 1 by root n plus 1. Taking LCM, surely xn minus yn tends to 0. Now, modulus of f of xn minus f of yn equals modulus of what is f of x? 1 by x square. So it is 1 by, means here xn is 1 by xn square. Okay, so it is 1 by xn square minus 1 by yn square because f of x is 1 by x square. So that equals modulus of 1 by xn square means n square minus 1 by n 1. So it is n plus 1 whole square equals to. Okay. For all xn, yn falling closed open 0. So here xn minus yn tends to 0, but modulus of f of xn minus f of yn converges to 1 means it does not tends to 0. So that implies f is not uniformly, that means by criteria f is not uniformly continuous on that. Means it is greater than some epsilon. Okay. So by the criteria of non-uniform continuity, here f is not uniformly continuous. If limit xn minus n equals 0 and the modulus of f of xn minus f of n greater than epsilon, then f is not uniformly continuous. Then according to that criteria for non-uniform continuity, here f is not uniformly continuous. So means, see here when the lower limit is changed, it is changed from 1 to 0, then on close to 1 infinity, the function is uniformly continuous, and on close 0 infinity, it is not uniformly continuous. Clear? Thank you.